Hello everyone! Today we're excited to take you on a comfort journey through the basic of graph theory. So graph theory is like a puzzle that helps us understand how things are connected. Think of it as a bunch of dots. We call them vertices. With lines connecting them, we call these edges. It's like connecting the dots of our digital and social lives. So today we'll explore these dots and lines, discovering how they can solve real-world problems from making sense of spreadsheets to designing efficient computing networks. So grab your magnifying glass and let's dive into the vibrant world of graph theory together. At the end of this video presentation, everyone should be able to comprehend the fundamentals of graph, concepts, and terminology such as vertices, edges, paths, and degrees. Second, understand graph properties including connectivity, planarity, and use of algorithms. Next is acknowledge the real-world application of graph theory across various fields and its role in solving complex issues. And lastly, verify Euler'S formula for the planar graph. So first, let's define graph theory. So graph theory is a branch of mathematics that studies the properties and relationship of graphs and provides tools and algorithms to analyze and solve problems related to graphs. Then, what is graph, by the way? A graph is a pictorial representation of sets of objects where some pairs of objects are connected by links. The interconnected of objects are represented by points, terms as vertices, and the links that connect the vertices are called edges. Formally, a graph is pair of V and E, where V is a set of vertices and E is a set of edges. Connecting the pairs of vertices, take a look at the following graphs. So the vertices are A, B, C, D, and E. And the edges are AB, AC, BD, and CD, and E. So let's proceed in its application. In electrical engineering, graph theory helps plan and optimize power grids, making sure electricity flows efficiently. And computer science is like a guide for designing smooth pathways and networks, ensuring quick and reliable data transfer. In science, graph theory models connections between molecules and fields, helping scientists understand complex biological systems. Linguistics uses graph theory also to decode language patterns and making machines understand and process language better. Generally, graph theory is like a problem-solving toolkit that pops up everywhere. It helps engineers plan circuits, computer scientists design networks, and study molecules, and linguists unravel secrets of language, making our world more connected and efficient.
Vertices and edges. Edge are straight lines that define the sides of the polygons that make up each face of the shape. Vertices or corners are points where at least three edges met. Vertices are the points or nodes, and edges are the arrows showing the direction. It's a useful way to model relationships where there are a clear starting and ending point. Directed and understand graphs. Directed graphs or big graphs depict relationship where edges have a defined direction like arrows pointing from one node to another. Understanding graphs involves comprehending how nodes are connected by edges, providing a visual representation of connections or dependencies within a system or dataset.
I'm Euler'S and adjacency. Adjacency and graph theory adjacency refers to the relationship between vertices or nodes in a graph. Specifically, it addresses whether two vertices are connected by an edge. There are two common ways to present adjacency. Degree of vertex. The degree of a vertex in a graph is the number of edges incident to it. Or in simple terms, the number of connections it has two other vertices.
Hi, I am Susan and that's about path. In graph theory, path in a graph seems a finite or infinite sequence of edges which joins a sequence of vertices which most definition are all distinct, and since the vertices are distinct, so are the edges. And now let's talk about cycle. Let be an edge in G between vertex E and W that is not in T. Now in T there is a unique way between V and W, then since E is not in T, that path does not use E. Therefore, that path together with E forms a cycle in G. A cycle built this way called a fundamental cycle.
A connected graph is a graph that is connected in the sense of a topological space. There is a path from any point to any other point in the graph. A graph that is not connected is said to be disconnected. This definition means that the null graph and singleton graph are considered connected while empty graph is odd. Complete graph is a simple undirected graph in which every pair of distinct vertices is connected by a unique edge. A complete digraph is a directed graph in which every pair of distinct vertices is connected by a pair of unique edges, one in each direction.
Planar graph. A planar graph is a type of graph that can be drawn on a flat surface, such as a piece of paper, without any of its edges crossing over each other. A drawing of a planar graph that has no edge crossing is called a plane graph or a planar embedding. Graph algorithms. Graph algorithms are a set of algorithms that are used to process, analyze, and understand graph data structures. Graphs are mathematical structures used to model relationship between objects, where the objects are represented as vertices or nodes, and the relationship between them are represented as edges.
In the planar drawing of a graph, the edges divide the graph into different regions called faces. The exterior region surrounding the graph is also considered a face, which is called the infinite face. The following relationship, called Euler's formula, in a connected planar graph drawn with no intersecting edges, let be the number of vertices, the number of edges, and the number of faces. Then, vertices minus edges plus faces equals 2. Example, there are 5 vertices, 9 edges, and 6 faces, including the infinite face in the graph. By substitution of values, 5 equals to 9, plus 6 equals to 2.
In conclusion, graph theory, a versatile mathematical framework, encapsulates a profound understanding of interconnected systems. It serves as a universal language to modeling relationships, providing insight into connectivity, contrariety, and algorithmic problem solving, from representing diverse networks to unraveling optimal paths and structural similarities. Graph theories in adaptability and efficiency make it an indispensable tool across various domains. In essence, it's the key to unraveling the intricate web of connections that define our complex world.